Welcome. Today we'll derive the expression for the electric field at a point on the axial line of an electric dipole. An electric dipole consists of two equal but opposite charges separated by a small distance. Let's set up our problem. We have a positive charge plus q and a negative charge minus q separated by a distance 2a. We want to find the electric field at point P, which is at a distance r from the center of the dipole along the axial line. Let's start with the basic equation for electric field due to a point charge. The electric field E equals kq over r squared, where k is Coulomb's constant and r is the distance from the charge. For our dipole, we need to consider the distances from each charge to point P. From the positive charge, the distances are minus a, and from the negative charge, it's r plus a. This gives us two electric field components. The net electric field is the vector sum of these components. Since they're along the same line, we can subtract their magnitudes. This gives us E net equals kq over r minus a squared, minus kq over r plus a squared. 4 points far from the dipole, where r is much greater than a, we can use the binomial approximation. This means r plus or minus a squared approximately equals r squared plus or minus 2ar. After several steps of algebra, combining terms, and using the binomial approximation, we arrive at our final expression. The electric field equals 2kp over r cubed, where p is the dipole moment equal to q times 2a. This expression shows us that the electric field of a dipole decreases with the cube of the distance, much faster than the inverse square dependence of a point charge. The direction of the field is along the dipole moment vector p. Welcome. Today we'll derive the expression for the electric field at a point on the equatorial plane of an electric dipole. An electric dipole consists of two equal but opposite charges separated by a distance. Let's set up our problem. We have a positive charge q and a negative charge q separated by a distance 2a. We want to find the electric field at point P, which lies on the equatorial plane at a distance r from the center of the dipole. Let's recall that the electric field due to a point charge is given by Coulomb's law, E equals kq over r squared in the radial direction. At point P, both charges contribute to the electric field, and we need to consider their vector components. The distance from each charge to point P is the square root of r squared plus a squared. Due to the symmetry of the dipole, the horizontal components of the electric fields cancel out, while the vertical components add up. The vertical component of the electric field due to each charge is vertical equals k, qa over quantity r squared plus a squared to the 3/2 power. The total field is twice this value, since both charges contribute equally. We can express this in terms of the dipole moment p, which equals q times 2a. This gives us our final expression. The electric field equals kp over r cubed for points far from the dipole, where r is much greater than a. In conclusion, we've derived the expression for the electric field on the equatorial plane of a dipole by considering the vector components of the fields from both charges and using the symmetry of the system. This result is particularly useful in understanding molecular interactions and the behavior of polar molecules. Welcome. Today we'll derive the expression for the electric field due to an infinitely long, uniformly charged wire using Gauss's law. Let's start by visualizing our setup. We have an infinitely long wire with a uniform linear charge density lambda. The electric field lines point radially outward from the wire, since we'll assume a positive charge. To use Gauss's law, we'll choose a cylindrical Gaussian surface coaxial with the wire. Let's label the important parameters of our Gaussian surface. We'll call the radius of our cylinder r and its length L. Due to the symmetry of our setup, we know that the electric field must be radially outward and equal in magnitude at all points equidistant from the wire. Now, Let's apply Gauss's law. Gauss's law states that the electric flux through a closed surface equals the enclosed charge divided by epsilon naught. The flux is the surface integral of E dot over the entire Gaussian surface. Let's consider the flux through each part of our Gaussian surface. Through the curved surface, the electric field is perpendicular to the surface, so E dot equals E times da. Through the end caps, the electric field is parallel to the surface, so E dot equals 0. For the curved surface, the area is 2 pi RL. The enclosed charge is lambda times L. Substituting these into Gauss's law, now we can solve for E. The L's cancel out, and we can multiply both sides by 1 over 2 pi r. This gives us our final expression. The electric field equals lambda over 2 pi epsilon naught r. This result shows us that the electric field falls off as 1 over r, which is different from the 1 over r squared dependence we see with point charges. This is because the infinite wire can be thought of as a continuous line of point charges, and their combined effect leads to this 1 over r dependence. Today we'll derive the expression for the electric field due to a uniformly charged infinite plane sheet using Gauss's law. Let's start by visualizing our setup. We have an infinite plane sheet that's uniformly charged with a surface charge density sigma. Due to the symmetry of this setup, the electric field lines will be perpendicular to the plane. To use Gauss's law, we need to choose an appropriate Gaussian surface. We'll use a cylindrical surface, often called a pillbox, that intersects our charged plane. Due to the symmetry of our setup, the electric field will be equal in magnitude but opposite in direction on both sides of the plane. Now, let's apply Gauss's law. Gauss's law states that the electric flux through a closed surface equals the enclosed charge divided by epsilon naught, the permittivity of free space. Let's calculate the enclosed charge. The charge enclosed is the surface charge density sigma times the area of the circular cross-section of our Gaussian surface. Now, let's evaluate the electric flux. Due to the symmetry of our setup, the electric field is perpendicular to the top and bottom faces of our cylinder and parallel to the curved side. The curved side doesn't contribute to the flux because the electric field is parallel to it. The flux through the top and bottom faces is E times the area of each face. Let's put it all together. Substituting these expressions into Gauss's law, 2E A equals sigma A over epsilon naught. Solving for E, we get our final result. The electric field equals sigma over 2 epsilon naught. This is a remarkable result. The electric field is constant and doesn't depend on the distance from the plane. The field points away from the plane if the charge is positive, and toward the plane if the charge is negative. Welcome. Today we'll derive the expression for the electric field due to a thin spherical shell using Gauss's law. We'll find the field both outside and on the surface of the shell. Let's start by considering our spherical shell. Here we have a thin spherical shell of radius r with a total charge q distributed uniformly over its surface. To use Gauss's law, we'll consider a larger Gaussian surface of radius r, where r is greater than r. Due to the uniform distribution of charge, the electric field lines are radially outward and have the same magnitude at all points on our Gaussian surface. This symmetry is crucial for applying Gauss's law. Now, let's apply Gauss's law. Gauss's law states that the electric flux through a closed surface equals the enclosed charge divided by epsilon naught, the permittivity of free space. Due to the spherical symmetry, the electric field is perpendicular to the surface at every point and has the same magnitude E. The area of our Gaussian surface is 4 pi r squared. Therefore, the flux equals E times 4 pi r squared. Now we can solve for the electric field. Substituting our flux expression into Gauss's law, we get E times 4 pi r squared equals Q over epsilon naught. Solving for E, we get Q over 4 pi epsilon naught r squared. What about the field on the surface of the shell? When r equals r, we simply substitute r for r in our equation. This gives us the electric field on the surface as Q over 4 pi epsilon naught r squared. Let's summarize our key findings. For points outside the shell, the electric field behaves as if all the charge were concentrated at the center. It follows an inverse square relationship with distance. And on the surface, the field depends only on the total charge and the radius of the shell. Welcome. Today we'll derive the expression for the electric field due to a thin spherical shell using Gauss's law. We'll find the field both outside and on the surface of the shell. Let's start by considering our spherical shell. Here we have a thin spherical shell of radius r with a total charge q distributed uniformly over its surface. To use Gauss's law, we'll consider a larger Gaussian surface of radius r, where r is greater than r. Due to the uniform distribution of charge, the electric field lines are radially outward and have the same magnitude at all points on our Gaussian surface. This symmetry is crucial for applying Gauss's law. Now, let's apply Gauss's law. Gauss's law states that the electric flux through a closed surface equals the enclosed charge divided by epsilon naught, the permittivity of free space. Due to the spherical symmetry, the electric field is perpendicular to the surface at every point and has the same magnitude E. The area of our Gaussian surface is 4 pi r squared. Therefore, the flux equals E times 4 pi r squared. Now we can solve for the electric field. Substituting our flux expression into Gauss's law, we get E times 4 pi r squared equals Q over epsilon naught. Solving for E, we get Q over 4 pi epsilon naught r squared. What about the field on the surface of the shell? When r equals r, we simply substitute r for r in our equation. This gives us the electric field on the surface as Q over 4 pi epsilon naught r squared. Let's summarize our key findings. For points outside the shell, the electric field behaves as if all the charge were concentrated at the center. It follows an inverse square relationship with distance. And on the surface, the field depends only on the total charge and the radius of the shell. Let's solve a problem involving electric forces between charges arranged in a square. We have 4 charges placed at the corners of a square with side length 0.05 meters. Let's draw our square and label the charges. Here's our square ABCD. At corner A, we have positive 10 nanocoulombs, at B negative 20 nanocoulombs, at C negative 10 nanocoulombs, and at D positive 20 nanocoulombs. We need to find the resultant force on the charge at point D. To find the resultant force, we'll need to find the individual forces from each charge and then add them as vectors. Let's start with the force from charge A on charge D. Since both charges are positive, this force will be repulsive, pointing away from A along the diagonal. Next, the force from charge B. Since B is negative and D is positive, this force will be attractive, pointing towards B. Finally, the force from charge C. This will be attractive as well, pointing towards C. Let's calculate each force magnitude using Coulomb's law. The force between 2-point charges equals Coulomb's constant K times the product of the charges divided by the square of the distance between them. For the force between A and D, we have charges of positive 10 and positive 20 nanocoulombs, and the distance is the diagonal of the square, which is 0.05 times root 2 meters. This gives us a force of 7.2 times 10 to the negative 4th newtons. Similarly, for the force between B and D, we have charges of negative 20 and positive 20 nanocoulombs at a distance of 0.05 meters. This gives us 14.4 times 10 to the negative 4th newtons. And finally, for the force between C and D, we have charges of negative 10 and positive 20 nanocoulombs, also at a distance of 0.05 meters. This gives us 7.2 times 10 to the negative 4th newtons. Now we need to add these forces as vectors. Let's break down each force into its x and y components. For the x component, we have FBD plus FAD cosine 45 degrees. For the y component, we have FCD plus FAD sine 45 degrees. Plugging in our values and calculating, we get a resultant force magnitude of approximately 12.4 times 10 to the negative 4th newtons. The direction of this force is approximately 32 degrees above the positive x-axis. Welcome. Today we'll solve a problem involving electric fields from multiple charges arranged in a square. We have 4 charges, Q, 2Q, 3Q, and 4Q placed at the corners of a square with side length 0.1 meters. We need to find Q given that the electric field at the center is 5.1 times 10 to the 3rd newtons per coulomb. Let's start by drawing our square. Here's our square ABCD. At corner A, we have charge Q, at B we have 2Q, at C we have 3Q, and at D we have 4 quetzales. And here's our point O at the center where we want to find the electric field. Let's analyze the electric field from each charge. First, note that the distance from each corner to the center is the same. It's equal to the side length divided by root 2. The electric field from a point charge is given by Coulomb's constant K times the charge divided by r squared, where r is the distance from the charge. Now let's look at the electric field from each charge. Each charge creates an electric field pointing away from itself. The magnitude depends on the charge value, but they all point through the center. Due to the symmetry of our setup, the net electric field at the center will be the sum of all individual field magnitudes. We can write this as E net equals K times the sum of all charges divided by r squared. Let's substitute our known values. We know K is 9 times 10 to the 9th, the side length is 0.1 meters, and the net field is 5.1 times 10 to the 3rd newtons per coulomb. Simplifying the right side, we get 10q times K divided by the square of s over root 2. Now we can solve for Q. After rearranging and simplifying, we get Q equals 1 nanocoulomb. So the value of our base charge Q is positive 1 nanocoulomb. Welcome. Today we'll solve a problem involving charged metallic spheres and Coulomb's law. Two oppositely charged identical spheres are placed 0.5 meters apart, initially attracting each other with a force of 0.108 newtons. When connected by a copper wire, the charges redistribute. Afterward, they repel with a force of 0.036 newtons. Let's use Coulomb's law. The force is K times the product of charges divided by r squared. For the initial attraction, we have F underscore 1 equals K, Q underscore 1 Q underscore 2 slash r caret 2. This gives us Q 1 Q2 equals 3 times 10 to the power of negative 12c squared. After redistribution, the repulsive force is F underscore 2 equals K Q caret 2 slash r caret 2. Solving for Q, the common charge, we get 1 mu c. Now, since the total charge is 2Q equals 2 mu c, we have two equations. Q1 plus Q2 equals 2 mu c, and Q1 Q2 equals minus 3 times 10 to the power of negative 12c squared. Solving this system, we find Q1 equals 3 mu c and Q2 equals minus 1 mu c. Let's solve a problem involving finding the point where the electric field is 0 between two positive charges. We have two charges, a 0.2 microcoulomb charge and a 0.8 microcoulomb charge, placed 0.15 meters apart. Let's visualize this setup. Here's our first charge, Q1, which is 0.2 microcoulombs, and here's our second charge, Q2, which is 0.8 microcoulombs. The distance between them is 0.15 meters. Since both charges are positive, they both create electric fields pointing outward. At some point between these charges, the electric field will be 0. This happens when the electric field from Q1 exactly cancels out the electric field from Q2. The electric field due to a point charge is given by Coulomb's law. E equals K times the magnitude of the charge divided by r squared. At the point where the field is 0, the magnitudes of the fields from both charges must be equal. This gives us K times Q1 over x squared equals K times Q2 over d minus x squared, where x is the distance from Q1 and d is the total distance between the charges. Let's plug in our values. We have K times 0.2 times 10 to the negative 6 over x squared equals K times 0.8 times 10 to the negative 6 over 0.15 minus x squared. The k's cancel out, and we can simplify this to 0.2 times 0.15 minus x squared equals 0.8x squared. Expanding this out and rearranging terms, we get 0.6x squared plus 0.06x minus 0.0045 equals 0. This is a quadratic equation that we can solve using the quadratic formula. When we solve this, we get x equals 0.05 meters. Therefore, the electric field is 0 at a point 0.05 meters from the 0.2 microcoulomb charge, which is between the two charges. This makes sense because the larger charge has a stronger field, so the 0 point must be closer to the smaller charge. Let's solve a problem involving a charged pendulum in an electric field. This is an interesting case where we'll see the interaction between gravitational and electric forces. Here's our problem. We have a pendulum bob with a mass of 80 milligrams and a charge of 2 times 10 to the minus 8 coulombs. It's at rest at some angle in a horizontal uniform electric field of 20,000 volts per meter. We need to find both the tension in the thread and the angle it makes with the vertical. Let's draw a diagram of our system. We have a pivot point at the top from which our pendulum string hangs. The bob has both mass and charge. The electric field is horizontal and uniform, pointing to the right. The pendulum makes some angle theta with the vertical. Let's analyze the forces acting on our bob. First, we have the gravitational force acting downward. Second, there's the electric force acting horizontally due to the electric field. And finally, we have the tension force in the string acting along the string's direction. Let's calculate the gravitational force first. The mass is 80 milligrams, or 80 times 10 to the minus 6 kilograms. Multiplying by g, we get 7.84 times 10 to the minus 4 newtons. Now, for the electric force, we multiply the charge 2 times 10 to the minus 8 coulombs by the electric field 20,000 volts per meter. This gives us 4 times 10 to the minus 4 newtons. Since the bob is in equilibrium, we can write two equations. In the vertical direction, T cosine theta equals the gravitational force, and in the horizontal direction, T sine theta equals the electric force. To find the angle, we can divide these equations. This gives us tangent theta equals Fe over Fg. Plugging in our values and calculating, we get an angle of 27.02 degrees. Finally, to find the tension, we can use either equation. Using the vertical component, we get T equals Fg divided by cosine theta. Plugging in our values, we get a tension of 8.8 times 10 to the minus 4 newton.